Alright, what's going on, you guys? Another LeetCode video today. This problem's called in queens, and it's the problem of placing in queens on an n by n chessboard such that no two queens can attack each other. So it takes a little bit of chess knowledge. So basically what they want is, they're going to give us an integer n, right? So they want us to imagine some n by n chessboards, and they basically want us to return every combination of every configuration of in queens on that chessboard, in positions such that they can't attack each other. So if we look at these 4x4 chessboards here in this first example, you've obviously got to put 4 queens on there in that configuration, and it turns out there's only 2 options here, right? They can either be kind of staggered like this or like that. And those are the only 2 options. If you tried to put the queens anywhere else, they'd be in a configuration where they could attack each other, and that wouldn't be valid. So the time complexity, this is a pretty computationally expensive problem. We can tell because the constraints, n is only going to be 9 at most. So yeah, let's get into the whiteboarding. We're just going to do recursive backtracking to solve this. There's also a couple things that are helpful to understand, I think, before we get into the actual backtracking part of the algorithm. So yeah, let me just draw a chessboard here. So imagine we had a chessboard here, and this will just be, make this like a 4x4. So yeah, just imagine this is a chessboard, and we're gonna go over a few ideas, right? So the first idea is that, so what are the rules for a queen, right? A queen can basically move horizontally. So like if you had a queen right here, the queen can move horizontally, so anywhere as far as it wants this direction. It can also move anywhere as far as it wants up or down vertically, and it can also move as far as it wants diagonally, right? So, and that's in every diagonal direction, right? So as far as it wants. So that's the rules for a queen, right? So valid. So if there's a queen here, a queen here would be in the way. That'd be attackable, right? Same if it was like over here. Hopefully this is like a pretty straightforward part of the problem. It helps if you've played chess for this one. But anyways, yeah, that's the the rules for the queen. So being that they can attack anywhere horizontally, what does that tell us? Well, we can't have any queens in the same row or the same column. So the approach we're going to take here is we're basically just going to be iterating down each row of the board, right? So each row I, so we have like 0, 1, 2, 3. And we're just going to be trying to place a queen in each row, right? Because there can only be 1 queen in every row. So that's how we're going to be kind of iterating through the board. So there can only be 1 queen in a row, and then from there it's just a matter of figuring out, okay, well, there's only 4 options here, right, for each of these 4 indices. And how do you know which is like a valid option? Well, we're going to have some sets that help us basically when we're building a board to tell us, whether or not we've already placed a queen somewhere that interferes with this space, right? So say we're trying to put a queen here. Can we do that? Well, we're going to have 3 sets. We're going to have our first set is going to be, we don't need to have a set for rows, right? Because we're going through each row iteratively, but we need to have a set for columns, right? And that's pretty easy. Once we put a queen down on the board, we've got to mark the index of the column that's at. So we can do a O of 1 constant time lookup on, okay, has any queen gone in this column? Now it's a little bit less straightforward, right? So columns is easy, right? But there's going to be 2 other types of sets, right? And what are those going to be? Well, It's going to be for the diagonals, right? You can go diagonal uh, this on this diagonal axis, right? So we're going to call this diagonal. Let's see. So if you going back to like, you know, college, high school math for angles, this angle right here would be 45 degrees. So we're going to call this the 45-degree diagonal. And then likewise, you can also go diagonally in this axis, right, this way. So that we're going to call that one, you know, this angle is bigger. That's going to be the 135-degree diagonal. So that's just for naming, right? It doesn't actually like mean anything for the problem, but that's just to help. They are different, right? The diagonal that's the 135 is going to need different rules for the diagonal that's the 45. And let's identify those rules, right? So if we were you know, moving this way, like what do all of these cells have in common on this diagonal? Like, well, their indices, right? For the I index is this direction, by the way, is I. This direction is J, right? I is going to be our rows, J is going to be our column indices. Now, when we're going this way, each one of these cells, so we have 0, 2. 0 plus 2 is 2. Okay, this cell, we have 1 plus 1. 1 plus 1 is 2. This cell, 2 plus 0 is 2. Okay, so that's interesting. If we add up the indices, you get the same value for every cell in that diagonal for the 45 degree, right? So 3 plus 0, 3. So let's, you know, write that. We have 2, 2, 2, 3. Let's see, 2 plus 1, 3, 2 plus 1, 3, 4 plus 0, or I mean, yeah, 3 plus, this is, okay, I was like, what the heck? Yeah, this should be a 3. Okay, but basically every single one of those cells are going to have correspond to the same number when you just add I and J. So we're going to do I plus J to mark the diagonals pretty much. The 45 degree diagonals. And then what about the 135 degree diagonals? Well, so if we went this way, there's a little bit of a different pattern. It's similar, but it's different. So we have 1 minus 0. So hint, it's going to be the I, so it's going to be the row index minus the column index. So 1 minus 0 here is just 1. For this tile, 2 minus 1 is also just 1. So here for this 3, we have 3 minus 2, it's also just 1. So pretty much we're going to be doing I minus J to mark the 135 degree diagonals. So yeah, so we have a way now basically to determine for each row that we check iteratively, right? We're going to be going row by row, and then we're just going to check every cell in that row, and we're going to see if we can store it there, right? So, and we have these 3 sets that'll help us, and that's all we're going to need. So let's go over the recursive backtracking part of this algorithm. I know this is really hideous illustration. But yeah, let's go over the recursive backtracking, right? So let's do a 4x4 example. So we're going to start by basically just populating a 4x4 vector of strings, all with periods at first, right? And then in the first call for this recursion, we're going to be trying to put a queen in the first row, right? We're just going to be going down the rows. So go this way. We're going to try to put a queen in that first row. We're going to check that, you know, cell 0, 0. There's no other queens on the board, so that's going to work. And then our board will look like this. Okay, so for backtracking, we're basically going to be able to put a queen at every position in this first row because there's no other there's no other queens on the board yet, right? So there's nothing interfering with this first option. So I don't think I'll do this entire board because it's probably going to be a lot of steps to draw, but we'll get a decent way down this. So basically, yeah, just putting that in the next available position after backtracking it out of where we put it first. And then same thing again. And then same thing again. So this is just kind of showing how this works. Now let's move a step or a level down our recursive tree, so or recursion tree. This is like an imaginary tree that's kind of showing the board at each step of the recursion, right? So okay, so now we'd go this way, and basically we just did this first row. Okay, but now we have to do the second row, right? So that queen that we placed in the top left is going to stay there. Okay, and then it's like, okay, can we put a queen here? No, so we would skip that. Can we put a queen here? No, our diagonal 135 set would tell us that there's a queen here, so we can't go here. What about here? This would be valid, right? So we can put a queen here. All right, so, and then there's one more place we can put one. We could also put one there. So let's draw that. Okay, so yeah, that's pretty much, I mean, if you kept going down from this path, we can already see, because we saw that there's only 2 valid configurations for a 4x4 board for the in queens problem. If you have them in the corner, it's just not going to work at all. And basically, there's not going to be any recursive call. And for this board to get added, we have to make it all the way down to this level. So basically, these are never going to lead to anywhere in terms of being added to the result of our what we're returning in the end, which is just going to be basically a vector of boards like this, that where we've gone all the way down, and we were successfully able to place. There must be a queen placed in each row, right? That's like a rule. So, and basically, you would get both solutions down these paths. So in terms of the time and space complexity, the time for this problem is just going to be big O of n factorial, where n is that integer n they give us, and that's because this problem is really, we have to place a queen on each row, and there's n factorial basically permutations of at most where we can place those queens in every row. So for the space, this is going to be big O of n, because the height of our recursive stack is going to be n tops, right? Because we're basically just going row by row down each branch, right? So yeah, and also, we have those sets for the columns and then the diagonals, but those are also going to be linear with respect to n. So still big O of n with the recursive stack and with those sets. And that's just auxiliary space, right? Obviously there's, if you're considering the space of the solutions as well, you're going to have some more. It's going to be bigger, but I'm just considering the temporary space that we're going to be using in our functions, right? Excluding that final space for the result. But anyways, yeah, let's get into the code here. So the first thing that we want is just that vector of strings for the final result, right? That's like multiple boards, multiple board configurations. Each board is just a vector of strings, right? So we need that too. So it's a vector of strings, and we'll just call it board because we're going to need at least one board, right, to seed our recursion. The boards are going to have in rows, and they're going to have in dots on each row, right? So we can use the string constructor inside of the vector constructor like that to create the board, a 4x4 or a in by in board, right, of some arbitrary size n. So we also need an unordered set for the columns, and then also for the both diagonals, right? So there's a 45-degree diagonal, and I'll call that diagonal 45, right? And then we have a same for the 135 diagonal. Okay, so now we just need to seed that recursion, right? I'm not quite sure what all of our parameters are going to be, but let's just call that function there and then return result. So let's write that function signature to get an idea of what the parameters will be. So void, I'm going to overload the solve in queens method for our recursive backtracking method. So that'll be private method also. So we're gonna take an integer I, right, to know what row we're at, and then we're gonna need all of these unordered sets, right? We're basically gonna need all of this stuff. That's like all of the rest of our parameters in a nutshell. So I'm just gonna go ahead and copy those. And all of these need to be by reference, and we also don't want to have any constructors, right? But otherwise this is looking like it's going to be okay. So there we go. And then, yeah, let's add all of these are going to be by reference. So, and that's just to avoid unnecessary deep copies, because that gets very expensive in recursive backtracking like this, with a permutations problem. So let's see. So first thing we want to do is let's just check if we're at the final row, right? Because if we've made it down to the final row, we basically know that we were able to place in queens, right? We were able to place a queen on each row. So we need to add this board to the final result. So we're just going to say if I is equal to board.size, right? Which is synonymous with n. If it is, then we are going to push back this board configuration to the list of boards in our result. So, or vector of boards. So res.push back, and then board. And then we're just going to return, obviously, because there's no more rows, no more queens to add. So if we're in the middle of trying to populate this board or trying to, put a queen on a certain row, well, we're going to iterate through each basically column in this row. So we'll say, I'll use J to indicate that we're going through the columns. Also say J is less than board 0 dot size. So while it's less than the size of a row, right? So we could also just pass an n, but just being very specific there with, or verbose about what we're doing. So, so for each column in this row, we're gonna check right? We basically need to check each one of those sets that we have, right, to see if this is a valid column to place the queen. So we'll say, so calls dot, and we'll just use the contains method on calls. So if it contains j, right, then, and we don't have to check the rows, by the way, because you know we're just going through row by row. Every row has to have a queen. So and whenever we're at a row, it's like we've never seen this row before. So so if calls contains j, or we want to check our diagonal 45, and the rule for diagonal 45 was just adding I and j. So so contains I plus j, and then also our diagonal 135, and the rule for that one is I minus j. That's how we're labeling those diagonals. So yeah, so if any of those sets has something that a queen that can attack the queen and for the current column, we can't put it there. So we've just got to continue to the next column, right? Otherwise, we can put a queen here. So let's go ahead and add the you know, that column. So to indicate for the next rows, right? Like you can't put we've got to indicate to the next rows by, you know, adding these indices to these sets, right? So we're going to insert the column for the diagonal 45. We're going to insert that also, and it's just I plus j. Diagonal 135. We're going to insert, so just for everything, that's going to be I minus j. And then finally, let's set the queen on the board. So we can just do board I j equals capital Q, because that's the syntax they use for their board. And then yeah, after that we just call the recursion. So it's going to be solve in queens on, and then we just pass in each of those. We want to go to the next row, so we do have to increment I. Res board calls diag 45 diag 135. Okay, and then there's backtracking too, right? So we've got to backtrack the queen that we just added, right? So that we can try to add a queen in the, you know, the next available spot for this row. So we're basically going to have to do the inverse of this, right? So we're going to have to, and I think it's erase for a set for constant time. So erase, we're just erasing all of that, what we just did, and then setting the board back. So that's the backtracking. So then for the next iteration, we can try the next spot, you know, the next permutation for this row. So hopefully that makes sense for this problem. We just have to see this recursion, and we're pretty much done. So it's going to be 0, let's see, res board. So quite a few parameters here, but can't really get around that. It's best practice in C++ to have everything in as parameters for recursion, no global variables. So anyways, yeah, let's run this. So hopefully this video helps you understand this problem better. If it does, leave a like and subscribe. I'll see you guys in the next video. Peace.